All right, so let's start. How you guys doing today? Good. Good, thank you. All right, so I'm going to move on to the last half of the second part of the chapter 6 today. So please make sure you guys keep watching the YouTube video. But this is the second half of the chapter 6. So if you look at the second half of chapter 6, it talks about the EQ. So this is the constant equilibrium constant number. So this is your way to put K and equilibrium here. So as we know, when we have chemical reactions, you always consider the ones on the right side as products, and the one on the left side will be reactants. So if this is the case, we know sometimes it's not always going forward, but also the other way, reverse direction at the same time. So we want to find out at which point there will be at equilibrium status. So even though it's go both ways, try to remember the one on the left side is reactants, and one on the right side is product. That's kind of something you may need to remember. Okay. So if this is the case, what I mean by this is small letters are just coefficient numbers for each A, B, C, D. And this is obviously reactants products over here. So whenever you try to get this number, A, equilibrium constant, just you need to put the products over reactants, but you'll be told by this coefficient number here. So what I'm going to do is I'm going to copy these two products here, but remember whenever you do the equilibrium constant, they tend to use the number for concentration. So for concentration for C and D, your products, we'll put the bracket on. So if you put a bracket on your products, it means it's concentration number. So if it's 1 molar, there will be 1 molar there. Okay? So same thing here. And make sure this will be powered by its coefficient number, C. And also, you have the reactants over here at the bottom, A. This will be also powered by its coefficient number, A. So, for example, if we had maybe 1, 2, 2, 3, for example, and maybe concentration is 1 molar, 1 molar, 2 molar, 2 molar. All you need to do is, oh, by the way, I'm not going to do this mathematical problem on this. It's just for your information. This concentration, right? So the 2 molar, 2 molar. 1 molar, 1 molar. Okay, just copy those numbers. And coefficient number is 1, 2, 2, 3. So it'll be 1, 2, 2, 3. So you can solve for the equilibrium constant. I'm not going to do this once again, but this is for your. So this is how you can get this number for equilibrium constant. It makes sense so far, right? Okay, perfect. So if that is the true, if that really meaning for concentration for product and reactants, if you think about it, it's actually quite simple rule they follow. If you think this number is really big, much bigger than 1, but this is much bigger than 1, okay? That means, like I said, this is about the concentration. So if this is much higher than 1, your equilibrium constant number is much higher than number 1. Means it's product over reactants. So you have a really high number on products, very low number on reactants. That makes really big number, right? Obviously. So that means at equilibrium point, you're going to have a lot of products when you have a really high number for KEQ, equilibrium constant. Kind of makes sense, right? Because this is because of the concentration we use to measure theta mi for the KEQ. So the other way, if you have your equilibrium constant value is a lot smaller than 1, that actually means you have a very small numbers of, we can say the concentration as well, of the products, but if a lot of reactants still not doing anything. It doesn't do much of a forward direction there. So it will be very low number. Okay. So if you look at the numbers for the equilibrium constant, you can actually find out, oh, this reaction is favor the products or favors reactants. If it's a very low number, will favor reactants. If it's very high number, will favor the products at the equilibrium points because of the equation. Kind of makes sense, right? Okay. Yes. Perfect. So if that is the case, then maybe I can give a number for one example here. This is what we did on previous weeks and the Monday. Okay. So we always assume this is both way now, not this one. But still this is reactants, one on the right will be products, right? Okay. So this is what we did on the week before the exam, also the Monday. Let's say if I give you a number for this one, obviously this is just 1, 1, 1, right? So KEQ, concentration of carbide 1, ethylene, carbide 1 times hydrobromic acid, carbide 1. And let's say this number is equal to 7.1 times 10 to 7. So think about it. If your value is over here, based on this chemical reactions, your number for equilibrium constant is very high, 7.1 times 10 to 7. Then you can say at the equilibrium point, you're going to have which one a lot more than the other, left or right. It's very high number for equilibrium constant. So it'll be this one, right? Perfect. It's pretty simple, right? So you can say even some realistic chemical reactions, you can always assume which direction is more favored. So it will be more, forward reaction is much stronger to make the products. That's why at the equilibrium point, you get a lot of numbers of products. Yeah. So first again. Okay. So if that is the case, maybe now you wonder what determines the K at equilibrium. So this is determined by Gibbs free energy. Gibbs free energy. I'm not going to talk about what this is. All you need to know is how you can use this one. The reason why I'm not going to talk about what this is, because it takes me 2 hours to explain. So basically what it really tells you is, it will tell you if your reaction is going to be spontaneous or non-spontaneous. You guys kind of remember this, right? From thinking 1 or 2, okay. What I mean by that is the, this is the, so you have a Gibbs free energy of the products minus Gibbs free energy of reactants. If that makes change in Gibbs free energy, right? For sure. This delta sign means it's change in something. So delta G means it's change in Gibbs free energy, because we did subtraction from products to the reactants. So the change in Gibbs free energy is negative. That means is spontaneous reactions. If it's positive, this is going to be non-spontaneous reaction. So this is somewhat governs which direction this reaction will be favored or shift to the certain way in chemical reactions. Okay? So this is something you can try to remember this one. So when this is the negative and you're changing this free energy, we're gonna call this exergonic reactions. When it's positive, we're gonna call this endergonic reactions. Okay. So those are the terms you may want to be familiar with later this semester, because this is what governs the which direction reaction favors to proceed. So so far so good, right? Okay, so this is pretty good enough for the some thermodynamics part of your chapter 6. This is something you don't have to know for your exam. So I'll just tell you, like you just listen to it. Okay? So this is the delta Z naught means this naught means this delta Z was measured as standard condition, like 180 atm, and what concentration, what specific temperature, and pure compound, and so forth. Okay. So this is a kind of relationship. This is how I meant by how this Gibbs free energy will affect your KEQ over here. Okay, so it is going to be another way you can do this way. This is just anyway. So you can take a look. You can actually tell how you can find that either equilibrium constant from delta Z or equilibrium constant to the delta Z either way. Okay? So this is the relationship they have in your chemical reactions. But certainly you don't have to know for the exam, but there is a quite strong relationship between these two. This is how. So if this is the case, there's one more thing I kind of want to remind you of from the Jankin 1 and 2. I hope you guys remember this. When we start talking about delta Z here, we have delta H and delta S. You guys remember the kind of, so this gives free energy. Do you guys remember what this is? It's enthalpy. Do you guys remember this? Enthalpy. This is enthalpy. This is entropy. Okay. So gives free energy. Once again, I'm not going to talk about what it is, but the change in those two will indicate spontaneity of the reactions. That's all you need to know. The enthalpy indicates if you're going to be exothermic reactions or endothermic reactions. So exothermic reaction means is the heat energy is released from the system. The system is just a certain like a group of compounds in interaction for the chemical reactions. Everything else is surroundings. This is the system. This is maybe you're doing small chemical reaction in the maybe flask. That flask may be your system. Everything else outside the flask will be your surroundings. So maybe technically the whole universe except that part. So if the energy goes out in form of a heat, we call this exothermic reactions. Literally it says exo, like we saw exergonic reaction in this one too. Endo means it's actually going in. So the form of a heat energy going into the system, so endothermic reaction. So entropy usually indicates the degree of randomness or disorderliness of the system. So let's say you have a high entropy. That means that there's very high disorderliness in the system. And if it's very low in entropy, means everything is well organized in the system. So very easy way to determine what might be the entropy energy in chemistry is the measure of their kinetic energy. So if it's moving at a certain temperature really fast, means they're really high in entropy, because it tends to have very disorderliness in the system when it moves really fast. But maybe it's very cold temperature, there's not much of a kinetic energy, most of the atoms or molecules are kind of stand still, not move so much, and we can kind of assume, oh, maybe entropy in this system is very low at the moment. Kind of makes sense, right? Yeah. So just one more thing, this will be on the exam, so please listen to me carefully. Okay? So if you know this now, what those really means in terms of the change in those three terms. Here's the thing. This is also what we did briefly in your Gen Chem 2. Okay? You guys remember this? Okay. So based on your the conditions, thermodynamic conditions here, this is something I might put on your exam. Here's something. So I already told you this is when this is negative and gives changing gives free energy. This is spontaneous. So this will happen without any energy input there. It happens automatically when it's negative. When it's positive, it's not going to happen automatically, but you have to do something to the system so they can go forward in the reactions. So it's non-spontaneous. Okay? But maybe on the problem that might give you an exam, I'll give you number for those two. Oh, then this is temperature. This T means temperature in Kelvin. Okay. So remember this, you know what is the lowest possible temperature in the universe? What's that?
Absolute zero.
Perfect. 0 Kelvin. It's absolute zero. Perfect. So that means the absolute zero is the lowest possible temperature. But think about it. Then there will be no negative Kelvin temperature, because literally zero is the lowest you can go. So this number is always positive. Always positive. Okay? So remember this. This is always positive. And here's something you can do about it. So if this is a positive, but the multiple of these two will subtract the enthalpy change. So if this is a positive, and if your entropy change is a positive, okay, and your enthalpy change is negative, so this will be negative number minus multiple of positive number, which is also minus positive. So negative number minus positive number will be always negative. Always negative. If you have a number for enthalpy change is negative, entropy change is positive, it is always going to be spontaneous reactions. Okay? So it's the other way. If you have a positive number for enthalpy, and maybe this is the negative number for the entropy change, this is negative number minus negative number is actually plus to the plus. So this number is always going to be positive. So this reaction is always non-spontaneous. Whenever you have a number, positive number for enthalpy change and a negative number for entropy, eventually it will become positive. So it's always going to be positive number for change in Gibbs free energy. So you can tell if this reaction is going to be spontaneous or non-spontaneous. Not even just try out this equation here, but just know the symbols of your number for enthalpy or entropy. So for a second, we good? Let's move on. That's all I want you to know. So try to remember those bit of a three important terms in your thermodynamics, and maybe this one will tell you much about all the spontaneity in your chemical. All right. So first, good. You guys doing so well. Oh, so your time is pretty good. So the next one is. Let me actually double check because I'm missing that thing. Yeah, that was it. Perfect. Okay. So the next one is whenever you have I hope you guys remember, if you watch the Monday lecture on the YouTube, you'll see this one was the first part of Monday lecture. This is what we call radical reactions. Means we use the fish hook arrow, okay? So we can actually break apart, but they takes, if you look at the single bond here, it's just a small space where you can see a pair of electrons, so they can kind of hold each other with these covalent bonds. But when they break apart, they just take one for each A and B. So they takes the one on A and B. So we call this radical reactions. So if you do see those two radical fragments from this chemical breakage, you're going to need a certain amount of energy to do so. So this is the required amount of energy to break this bonds in the radical fragments is what we call bond dissociation energy. As you know, dissociation literally means it's kind of a break apart. So we call this a bond dissociation energy. So how many kilojoule amount of energy required to break these bonds, and how many moles of compounds and so forth will determine this one. So for this one, there's only certain things I want to tell you is this one. So do you guys remember when you try to break the bonds, you need to use the energy for sure, right? But when they make the bonds, they release the energy in form of heat. You guys remember this kind of ionic bond lattice energy? It's pretty much the same in here. So if you have any bio major here, you are perfect. Great. So you guys might know this. So this is adenosine, right? This is triphosphate. So adenosine triphosphate is what? ATP. Perfect. Perfect. This is good. So whenever you look at this one, definitely your bio major, I believe. So if you look at this one over here, this is one compound I can give you. This is ATP. There's another one, similar structure. But this is a bit more simple. Okay. I'm not going to put all the negative sign because you know what it is. So think about this one. Whenever you try to break the bonds here and here, you see this one is more easier. It's much easier to break this bond here than this one. Okay, because I don't know if it covers in the bio class. You remember phosphate, right? You guys remember this one, right? You guys remember this? So this one, you can draw the resonance structure, right? So when you break this bond over here, we normally do this with water. So if you break the bond with water, we call this hydrolysis, right? Hydrolysis. So if you do that, they'll become like this. Okay. So and they break apart, goes here, and one H will come here. Okay. So this is much easier because this can be in resonance structure. Resonance structure is they're taking to be more stabilized. So they can nicely distribute the electric potential among these electronegative atoms, which is the oxygen, so they can be more stable form. So here's the thing, but there are the 3 phosphate in a phosphodiester bonds here, but they're kind of wants to be stabilized. So even though they make a kind of bond here, right? But they can be better. They can be more stabilized when you break the bonds. So that means those bonds are weakly bonded each other yet. But when you break the bonds, they become one of the product that can have a stronger bonds. Kind of makes sense? Okay. So that means this is the reason why ATP is very high energy compounds. Because once again, if it's easy to break, it's easy to break, right? So you don't have to use a lot of energy into it to break it. But when you form the products, they will make a stronger bonds. That means they're going to release much more heat energy. So this is why the body used ATP as an energy source. We can use this energy for this one. And this is where we can see bond dissociation energy is a related kind of problem. So in other way, this is relatively speaking a bit much stronger bond here. So this glycerol 3-phosphate will become, when you break this bond, the same product over here, but just here, they become glycerol here, from glycerol 3-phosphate. They will not give us much of energy because you need to use quite a lot of bond dissociation energy into it. Then when they form the bonds in here and here, there's much of the difference in those two. So it's not much energy will come out there. Okay? So this is something you can also predict from the bond dissociation energy. But this is only a very small part of chapter 6. I'll move on. But I hope kind of makes sense though, right? Let me move on. Okay. That is the pretty much. So I'm thinking we get to very last part of the chapter 6. So if you look at this one, I'm gonna draw the energy diagram. I must warn you, I'm not a good drawer, so just be with me. But I'll try my best. So here's my I'm just gonna So here's the one thing that I show you in an energy diagram. So this is total energy of reactants, all the reactants. And then, so it's kind of tricky, but whenever you go to whenever we go to maybe this part, this actually indicates the total amount of energy of product actually. Because when you go over this, when you proceed the reaction from over maybe time, this is more where you can find the products actually. This is what you started with, which is the reactants over here. So so technically y-axis is just the total amount of energy, but you can say this is the reactants here, this is the products here. We're gonna go some of the intermediate steps there. This is what we're gonna do. So whenever you do this one, so once again, I'm gonna take this one first. Actually, this one tells said in the last of textbook, but the gap between these two is what we discussed. Delta Z over here. Okay, so this one over here. This is the point where we can transition state. So it's literally transition state. So whenever you make a new product, meaning you need to break the bonds in the reactants, you need to make the new bonds in the products, right? So whenever this is an example of this one, what we did this one. Okay, you guys remember this, right? So the one on the pi, electrons in the pi bond will take this one here. Okay, so whenever they try to break the double bonds and making a new bond to the hydrogen, and in that they will make a break the bonds in here to move on to the bromine here. So you can imagine it's also like a halfway done for each. Like it's a semi-broken, it's semi-breaking, semi-forming, semi-breaking kind of thing. So this is not yet done, but in a transition status. So we call this transition status. It's literally in the step, and this is why you see it's very high in energy. So think about it. If something is very high in energy, it means it's very unstable. It's very unstable. It's actually kind of makes sense. They're doing chemical reactions to be stabilized, but they're actually going to do this, but it's not done yet. So the maximum amount of energy to be happening, to make this happen, is amount of energy you need to make this reaction go forward. So we call this activation. I think you heard this too, right? In bio, activation energy. Okay. And this is a similar gas energy change, but with the double daggers superscription on the symbol. So this is what we call activation energy. So this is something they need to have to go forward. If you don't have this amount of energy, the reaction does not happen. Okay. So, but what do you mean? So you hear this is the delta G is negative. So what I just told you is what? It's spontaneous, right? But I'm telling you, you need to have activation energy to go forward. And now you have a question, right? What do you mean? It says just to go automatically. Here's the thing. So if this one goes, this will happen automatically, spontaneous for sure. But what I mean by this energy is this one. Do you guys, I don't know if I covered in Jenkins 1 or 2, but do you guys remember KMT, kinetic molecular theory? And also the part, you have a collision theory. So let me remind you. So we chemists in the back in like 19th centuries or 18th centuries, we didn't know how they make new compounds. We saw that every time in the reality in the nature, but we didn't know how. And the best substitution so far, still we see proving, is when they make a bond here. It's not just, I'm showing you this like an arrow here and here, but technically speaking, they're colliding each other. So whenever you have an ethylene where this bromic acid molecules are mixed, then they're actually moving. They're moving, but at a certain, they're moving so fast and continuously, and some molecules will collide each other. So if that colliding, or this is, so they're colliding because we have a room temperature. At a room temperature, they have a certain amount of the kinetic energy, right? And then also the heat energy, so they can keep moving. And when they collide together, here and here, they can make up bonds here. So we believe, so far in modern scientists, they actually make a physical contact. That's how we believe. We're not sure yet, actually, but this is, I think, still, there's one paper come out the January. They actually prove there's metallic bond is real. We don't know about this one. Anyway, so if that is true, if that assumption is true, that amount of energy, colliding, kinetic energy, the colliding, and those molecules will have a sufficient amount of energy to move over this hill. Then they can go forward. But for one of them that is the negative, they can go much easier because they can have a much more stable. They want to have a more collide and the heating. So here's the thing. That means they need to have a certain amount of kinetic energy to collide in a special amount of the force, which means energy. So if it can collide, like maybe not bonds, but it's maybe bonds, right? Something like this, okay? And one more thing you need to know is if they're not just colliding each other, they need to be colliding into the right position. So if this one wants to make this bond, then if it is coming in this way, for example, not going to happen, even though it's a strong enough force. So the temperature usually determines how fast, how many frequently they're going to collide in the right positions, and this will determine the certain amount of the activation energy you need to go through, and we'll go first anyway. Okay? So if that is the case, you're going to have a transition state here, so semi-bond, semi-breaking over here, and here you have just one step done, and it's the here. Yeah, please watch. I don't know if you watched the Monday one, but please watch this one. So when they bond to, this is polar reactions. The bromine will take the whole pair of electrons here, and this will become the hydrogen cation because there's no more electron. They took everything, and now this is the available electrons in the pi bond will attack this one. So now this one is 3 hydrogen over here. The hydrogen now is to here. Okay? But now it has 4, but it is only 3. So this will become positively charged. There's only 3 valence electrons around the carbon, but it's group 4. So that makes what? This will look for something positive. It's nucleophile. This is what we're looking for, something negative. This is the electrophile. So they do polar reactions over here, become new compounds here. So here, this is, and this is why you have also, so here is this is what we call a reaction intermediate. Intermediate here. This is the one with the carbocation. So this is kind of a product, but in the middle, because it's kind of happening 2-stepwise, sort of. Okay? And once they go over transition states, semi-bonding to hydrogen, now it's done. But you have intermediate, and they go over other with the bonding to the bromine. So it's kind of semi-bonding too. So this is second transition status over here, and goes to the final over here. Okay? Kind of makes sense. Okay. So one thing I can tell you is trust me, on your exam, this will become a lot easier. The type of exam problem I'm going to give you. So this is actually for your understanding. If you know what transition state or activation energy or the Gibbs energy change, that's pretty good. But if that kind of makes understandable, what you can say is here. So maybe in your exam, I can say, if you have this one, mole, and I can say which direction will go faster? The one with the high activation energy or one with the low activation energy? So the one with the lower activation energy means they only need to collide few times to make bonds, right? Because they don't need much of the energy. Means they don't have to collide much with the force or much less frequently. So this will go faster. The one with the lower activation energy will go much faster because it's kind of small amount of energy you require to make this reaction go forward. So maybe on your exam, I'll give you several examples with these two and say which one will go faster. You choose the second one over here. It's pretty simple, right? So here's the thing. Since you're a bio major, also it's covered in chapter 6. If you have the high activation energy, even though it's a negative delta G over here, the reaction will go slowly. It's spontaneously happening, but it's slow, right? So this is why we sometimes use in organic chemistry catalyst, in biochemistry we use enzyme. Okay? So as you can see, if you use enzyme in the biological mechanism, or if you use a catalyst in the chemical reactions, you're going to have a much lower activation energy, so you can have a reaction going much faster. So maybe this will take over days, but if you use catalyst, it happens in 5 seconds. So here's the thing. This is important, especially in the biological system. You guys know this, right? We have a homeostasis in our body, so we need to keep the temperature always constant and pH always constant. Everything is to optimize the function of your proteins, especially all the functions in your biological system. To do that, to get this activation energy overcoming, you need to have a high kinetic energy. Like I said, you guys remember this, right? That means biological system need to have an enzyme because they cannot increase the temperature. If they increase temperature, they'll kill the host. So they cannot do it. So either way, they choose is enzyme. So here's the thing, how they lower the energy, right? That's the question. So that makes sense. So you're not going to give a lot of heat energy to make it happen. How lower the energy? Here's the thing. So what I mentioned about make your chemical reaction going forward. First one was the energy, but the second one was what? Right position colliding. The enzyme does that too. So whenever you look at the enzymes in your bio classes, only thing that matters for this enzyme is always shape. So those shape of an enzyme will make the substrate right in the right position, and they don't have to use a lot of energy to colliding. They just got it there and make a new product and come out there. So this is why it makes such a small amount of energy but make it more efficient work to do. Thank you guys, that's it for today.